So let's start with water balance. All right, so that's you or somebody. Actually, I can add in the blue. A normal, typically a person is maybe about 50% water by mass. And that changes through the life cycle. Little babies are more like 70% water, which is why you always think of like little dewy skin baby. They're all kind of like really plump and all that. By the time your older age, you might be down below 50, more like 40 something percent. People tend to get all more kind of dried out looking. So it's that whole going from dewy baby to like kind of getting a little more desiccated looking. That is actually due to kind of the amount of water in your body. Obviously, balance meaning there's a certain amount. There's water coming in every day, water leaving every day. And it's usually about 2.5 liters. Obviously, that's got to be balanced. Otherwise, you're going to be either drying out or inflating with water. So let's talk a little bit about where that water is coming from and how we kind of control it. So let me. Where's the input? Where's water actually entering the body from?
Food and drinking.
So food is part of it. Like when you eat, and the numbers I'm going to put here are, obviously they're ballpark. Depends on your lifestyle, what kind of things you eat and drink. Solid foods are usually somewhere around 30%, right? Most of the foods you eat have some moisture. You're eating some lasagna. It's moist. What other ways do water enter your body?
Drinking water.
Water intake or liquid.
Liquids. And that's the main way. So I'm going to say like 60%. So in general, it's about, so between solid foods and liquids that you intake, that's about 90% of the water that gets added into your body every day. And then I have mentioned before, where is the other 10% coming from? That gets added into the plus side of this accounting.
Air you breathe in?
It's
The
related.
water that is reabsorbed.
No, the reabsorbed is still, it's just in your body already. So the air that you're breathing is related. I want something a little more, right? Because the air you're breathing is not, it's not the water in the air. What happens to that oxygen that you're breathing in? Metabolically, what happens to those O2 molecules that come
It condensates. The condensation.
No.
It's moistened and humidified, warmed in the nasal area.
No, go back to like the first few weeks of the class. Why do you breathe? Why do we have to breathe? What's the whole point of breathing? We talked
Cellular
about
respiration.
Yeah, that oxygen. What happens to that oxygen?
Turns into water.
Turns into water. Remember? When you're in the mitochondria, we had the electron transport chain. We had NADH. Sends in the 2 electrons go into the electron transport. And those electrons at the far end of the electron transport, it was 2 H pluses plus oxygen plus 2 electrons becomes an H2O. This was the final step of cellular respiration. And this metabolic water that's being created as part of cellular respiration is actually quite a bit. It's like about 10% of the water that's being added to your total balance every day. So cellular respiration. Cellular respiration is adding in. For some creatures, like if you're in the desert and you see the little kangaroo rats or something, they actually don't really have to drink at all. Just from their solid foods and their metabolic water, as well as having super duper efficient kidneys, that's all they need to stay hydrated. It's actually kind of trippy. If you look at a kidney in a kangaroo rat, these little rodents that are optimized to live in the desert, their loops of Henle go down much deeper than the loops of Henle in a human. And they create a much, much more intense osmotic gradient as you go down into the medulla of the kidney, which means their kidneys are way better at sucking water back into their body than ours even. So that's the input. How about the output? How does water leave the body? And again, this is obviously going to depend on your activity and the weather and everything, but ballpark, what are the main things that are exits of water?
Exhalation.
Yeah, so we talked about every time you breathe out, water is leaving your body. That was the whole point of breathing on the glass. And your skin as well. In general, your skin is pretty waterproof. You've got these like glycolipids that kind of keep you relatively waterproof, but there is still some moisture that leaves through the skin and obviously through your breath. So that, the number I have from one of my books is, it sounds really precise, but again, take it as a ballpark. 28% lungs and skin. How else do we lose water?
Urination.
Well, urination. That's like maybe 60%. And obviously this is adjustable. What other ways?
Sweating.
Yeah.
Oh wait, that's lungs and skin. Never mind.
So when I'm talking about skin, I'm talking about evaporation through your skin because your skin isn't totally waterproof. That you are liquid in here, and then there's some just water that is managing to leave the skin just because your skin's not totally waterproof. That's very different from perspiration. Perspiration is secreted by these little eccrine sweat glands. So I'm going to say here, again, this is going to depend obviously on how hot you are, but I'm going to say 8% perspiration. Let me spell it right. Right, this is for cooling. This is not just random, like if your skin isn't perfectly waterproof, so you're dehydrating. This is intentional. You're putting water on your skin to cool off for evaporative cooling.
How about, sorry,
Say it again.
how about via the lacrimal gland, the tears and
Oh, actually, I mean, I don't have that on here, but that would be in there too. That is.
and salivation via tongue?
That unless you're spitting on people, you're kind of swallowing them back in. But if you're spitting, the other one I'll write here is feces. Unless you are totally constipated and you can't really poop out rocks, there's got to be some moisture content in there for you to kind of keep the stuff moving through your colon and get it out of your body. So I've mentioned this word before, but I'll mention it again. There's around 1 liter that we call insensible water loss. One liter per day, I should say. So the basic idea here is, you can control urine and stuff like that, but no matter what, even if your body is trying its best to conserve water, you are going to lose about 1 liter a day through evaporation through your skin, from your exhalation, from whatever minimal perspiration your body is doing to kind of maintain its temperature. So you can live a long, like everybody here could probably survive a month without eating anything. If you did not eat any food whatsoever, you would not be happy. But you would start first, you'd go through all of your fat stores and probably then start kind of breaking down like lean body tissue and stuff. But probably at the end of a month, you'd still be alive and you'd be able to kind of recover. Assuming if you're developing, if you're a little kid, it can be more dangerous because you can get permanent damage if things are developing. But in general, we're all pretty safe about not eating for the couple of weeks. Drinking is very different. Like if we did not get any water at all for a week, we'd probably all be dead. So it's much more important to make sure you have a source of, constant source of water to stay hydrated. So I think this idea of insensible water loss, I like to bring it up just because it's your water is much more critical than food. What other things do I want to say about this? We can talk a little bit about, being thirsty. Thirsty happens, we saw that it can happen from ADH, the hypothalamic thirst center. It happens when, blood osmolarity. If your blood osmolarity is starting to go up, that's going to be a sign to your hypothalamus that I'm thirsty. I should bring water in. Or if your blood volume is going down, that's going to be a sign to your thirst center that you're thirsty and you want to drink. Those are things that are, again, going to create behaviors that increase this intake of liquids here, so you keep your water balance. So when you think about what does it mean to be thirsty, it's actually, there's actually little sensors that are looking at osmolarity. And if osmolarity is getting too high, that's a sign that your brain turns on its thirst. Or if, again, your blood volume is getting low. What else? We didn't really talk about perspiration much. For your temperature control, because we did talk a little bit when we talked about looking at the exhaled air. We talked about, we lost water and we also lost heat. If you remember that, the water, the air you breathed out had more water and was hotter, which means you're losing both water and heat from every breath. When I was reading some people's labs, people talked about this as being part of temperature regulation. And it might or might not be. Like In humans, the sweating is one of the main ways that we do temperature regulation if we want to cool off. Other mammals, like a dog, they don't have sweat glands like we do. For them, panting, getting rid of excess heat through their breath is actually a really critical part of their temperature control. There is evidence that humans do also use breathing as a way to get rid of heat, but it's definitely not as important as sweating, and it's not nearly as important as it is in other mammals like dogs and stuff, where they use panting as a primary cooling mechanism. So just kind of as an aside there. So water balance. What else do I want to say about water balance? I think that's it. Obviously, urine is the one thing that you can adjust dramatically here. That's the whole point of today's lab. You know, if you are drinking a big gulp of water, a whole bunch of H2O is coming in, you're going to have to really increase your urine output to keep this balance. If, on the other hand, we don't have much water coming in and we're trying to keep ourselves from dehydrating, we're going to have to really slow down the urine production. And so that's something that's like at the core of, you know, looking at the volume of your urine today in the lab, is this idea of water balance. You know, it's the kidneys that are obviously creating the urine and turning on or off those little aquaporins in the collecting ducts. I should mention, the last thing I'll mention on this, when we talked about blood pressure meds, so far we've talked about the beta blockers and why they're useful. We've talked about ACE inhibitors and why they're useful. And again, the one other drug that we haven't looked at specifically are diuretics. So one of the classics are what are called loop diuretics. Examples of this would be like Lasix and stuff like that. The way that these work, it's actually pretty cool. If we think about the nephron, you know, the proximal convoluted tubule, the loop of Henle, distal convoluted tubule, collecting duct. And again, remember we have like from 300 milliosmolar all the way down to like 1200 milliosmolar. And that gradient, having that really salty medulla, is how your kidneys work to reclaim the water back into your body. What these loop diuretics do is these block the sodium pumps in the ascending loop of Henle. And if you remember, those little sodium pumps in the ascending loop of Henle were a critical part of creating and maintaining this gradient. Right? So if you block those pumps, you are going to not have as strong of an osmotic gradient as you get down deeper into the kidney, which means you're not going to be as efficient at pulling water back into your body, which means more dilute urine is going to leave. So you'll pee more. And again, peeing more is obviously going to lower your blood pressure. We talked about blood pressure being, you know, long-term control is your blood volume. So a loop diuretic works at the loop of Henle by messing with this gradient. So the collecting ducts are not in as a high osmotic region, and so not as much water gets pulled back even when you do open the aquaporins. Does that make sense? So yeah, they're kind of cool. You know, and I think it's kind of fun because you'll definitely read Lasix, a loop diuretic, and you're like, what? It sounds kind of weird, like loop. Sounds like something like a little Hot Wheel car is going to go and do a trick around or something, but it's actually the loop of Henle. So other thing I want to talk about is pH balance. You know, again, this is also, we've looked at this from the very beginning of the semester. We've talked about what's the kind of quick first defense against changes in pH?
Buffer system?
The buffer systems. So buffer systems, these, you know, there's the bicarbonate buffer system. There's phosphate buffer systems. And actually even proteins. Proteins have, you know, through those side chains, they have the ability to either take up or release protons as necessary to adjust your pH. So these are very fast, obviously. These happen almost instantaneously. The problem with buffer systems is they have a limited capacity, right? You have a certain amount, you know, we talked about bicarbonate buffer system, you know, H2CO3 dissociating into H plus, you know, HCO3 minus, and how the equilibrium would move one way or the other way depending on how much H pluses were around or taken away. But ultimately, it depends on some limited amount of the weak acids and bases to dissociate or reassociate. So, you know, if you overwhelm the ability of whatever amount of the weak acids and bases to do their thing, then they're no longer going to work. So they work almost instantly, but they have a limited capacity based on, you know, how much of the actual buffer is around. Another part of pH balance that we have talked about is your respiratory system. You know, this has to do with the fact that the CO2 is being transported with, you know, as bicarbonate, which is basic. So in the respiratory system, if you double your ventilation, what is that going to do to the amount of CO2 in your blood if you are hyperventilating?
It will
Blowing off
be
more
raised.
CO2.
Wait, so what's going to be raised?
CO2.
No.
No. Oh, oxygen, sorry.
Yeah, so
The CO2 goes down because you're blowing it off.
Go down. Remember from that breathing lab, if you're breathing deeply, you have less CO2 in your body. If you have less CO2 in your body, what is the pH going to do?
Increase.
Going to increase, right? So we have less CO2, which means less bicarbonate. So we can have the pH will go up by about 0.2 just by doubling your ventilation, which is quite a bit. If you have the ventilation, you're hypoventilating. that means the CO2 is building up. What's gonna happen to your pH of your blood if the CO2 and that bicarbonate starts building up?
Become more acidic.
It'll become more acidic. The pH can go down by 0.2. So like having or doubling your ventilation, breathing a little deeper or breathing a little more shallow can adjust your pH up or down by, about 0.2 up or down. This is over minutes. It takes a little time to change the overall amount of CO2 in your blood and bring the pH up or down. So buffer systems are like instant. Respiratory control is, over the course of a minute or two. This obviously has a limited capacity, right? You are not going to just keep breathing faster or slower for the rest of your life to keep your pH balance. So this is a way to adjust the pH in the moment, to bring it up or down. But there's one last thing that's going to be the ultimate long-term control of your pH, which is going to be we've mentioned this before. We mentioned it last class. What's the only way to get rid of like metabolic acids and things out of your body? These can readjust these weak acids and bases, but nothing actually leaves or enters your body. This also is adjusting the amount of CO2, but it's not really changing, like not getting rid of acids or anything, even if you're increasing the pH here. What's the only way to actually get them get the H pluses out of your body?
Urinary system?
Yeah, remember that was one of the core functions of the urinary system when we were describing what are the things it does for you. If you are too acidic, you're going to end up peeing out H pluses. Remember, that's why we said the pH of your urine is going to depend on what you've been eating, what your body needs to do to adjust its pH over the long term. Again, this is over hours, obviously, because you need to wait for the kidneys to do their magic and the nephrons. But here you can pee out bicarbonates if you're too alkaline. You can pee out protons if you're too acidic. So this is ultimately going to be the long-term control of pH here. This is kind of instant. This is also relatively fast, but both of these are more temporary fixes. They'll adjust things in the moment, but they don't do kind of the long-term fix of getting rid of acids and bases from your body to recalibrate and adjust your homeostasis for pH. So does that make sense? So what is kind of a homeostatic pH for a person?
7.45 or something like that.
The 7.4 is considered usually kind of the balance point, the target point for a pH. So as it changes, if you get to like 7.45, you are in what's considered alkalosis, if I can spell it. If you are below 7.35, you're considered acidosis. I should spell these better. So this is where you're going to start turning on these mechanisms to try to bring you back into the comfortable zone here. If you get above 7.8 or below 7.0, I'll actually do it in red. Like no longer compatible with life. So this is kind of the sweet spot. Below 7.35 acidosis, above 7.45 alkalosis. If you get above 7.8 or below 7, it's kind of becoming critically dangerous. So that's the basic story of pH. And again, the things to maintain this balance, again, the buffer systems, the respiratory system, and the kidneys. We can talk about, let's talk about hyperventilation. You know, when somebody is freaking out about something, you know, what's happening to them? What's happening to their pH if they're starting to like hyperventilate just because they're terrified or they're freaking out about something?
They're becoming more alkalotic or having alkalosis.
So like hyperventilation going to lead to alkalosis. What do you usually do for somebody who is going into alkalosis because they're hyperventilating?
Breathe into a bag.
Yeah, you have them breathing into a little paper bag. Why is that useful?
They would breathe in more carbon dioxide.
Yeah, it's gonna start increasing the carbon dioxide and it's gonna bring their pH back down, right? If you start increasing the CO2 in their body again, that's gonna bring their pH back down where it should be. So this also constricts vessels that go up to your brain, which is why you probably noticed when you did that experiment where you hyperventilated and held your breath, like the first moment is like, whoa, you get all like lightheaded and kind of gets major head rush. So pH, any questions about pH balance? Again, the main thing, we've just got those three things to remember. Buffer systems, fast first defense, respiratory system, and ultimately long-term urinary system. Again, urinary system is doing, because often people think, oh, urinary system, you're peeing out, it's getting rid of wastes. It's doing so much more critical things. It's your pH balance. Again, it's your water balance. It's your salt balance. It's doing so many important things. All right. So that is that.